Swayam Prabha. Digital India. Educated India.
We continue our analysis of convection dominated transport in the limit of high Peclet number, where convective effects are dominant in compared to diffusive effects. Okay. I had briefly explained to you what that involves. Okay. If you write the convection diffusion equation, for example, for the simplest case of a heat transfer from a heated surface, okay, where the velocity is only in the streamwise x direction, and you have a surface, it is at the same temperature as the fluid for x less than 0, the section for x greater than 0 is heated up to a higher temperature, okay, and you want to find out what is the flux of heat and get a correlation, a Nusselt number correlation for the temperature field. The convection diffusion equation has a familiar form, okay. Ux times partial t by partial x is equal to alpha times del square t, okay. Or alternatively, if I write it in vector notation, u dot grad t is equal to alpha del square t, okay. U dot grad t is the variation in the temperature along the velocity streamlines, okay. Grad t is the vector variation in temperature. When you dot it with the velocity direction, it gives you the variation in temperature along the fluid velocity streamlines, along the direction of the fluid flow. If you consider the high Peclet number limit, you might simplistically neglect the diffusion term and you will just be left with u dot grad t is equal to 0. In that case, the solution is just that the temperature is a constant along streamlines, but with that you cannot satisfy the boundary condition that the temperature has to be a different temperature at the boundary. The reason for that is because the change in temperature of the fluid near the boundary is due to the heat flux from the surface into the fluid. That heat flux is necessarily diffusive because there is no convection perpendicular to the surface. And if we just neglect the diffusion terms, we neglect that transport of energy perpendicular to the surface. Because of that, there is no conduction and there is no change in temperature. However, even when the Peclet number is large, so that the heat is transported, it is convected downwards rapidly by the fluid flow, close to the surface there will always be a region within which the diffusion is important, and within that region there will be a change in temperature, okay, due to conduction from the surface. The thickness of that region will decrease as the Peclet number increases, or the ratio of convection to diffusion increases. However, if you scale it by the correct thickness, that scaled equation will be independent of Peclet number even in the limit as Peclet number goes to infinity, indicating that within this thin region close to the surface there continues to be a balance between convection and diffusion even as the Peclet number goes to infinity. And we had, in the last class, we had derived what is the dependence of the thickness of this region just by scaling the cross stream distance by a boundary layer thickness delta. Once I have scaled the cross stream distance by the boundary layer thickness delta, I can put it into the equation, and the diffusion term is proportional to 1 over delta square. In this particular case, for the flow past a flat surface, because the velocity increases linearly from the surface, the convection term is also proportional to delta. Okay. So, the convection is proportional to the boundary layer thickness itself, diffusion is proportional to 1 over the boundary layer thickness square, okay, because you have a second derivative in the Laplacian of temperature. If you balance those two, you will find that the boundary layer thickness goes as Peclet number to the minus 1/3, okay, because on the left side in the convection term, if I scale it, I have a Peclet number times delta, because the velocity itself is delta close to the surface. Right side I have 1 over delta square, and balancing those two, you just find that the boundary layer thickness goes as Peclet number to the minus 1/3. Last class I had tried to also give you a derivation of a similarity solution. That similarity solution was based upon the justification, okay, that if I scale by the boundary layer thickness for the cross stream direction, then the cross stream diffusion becomes much larger than the streamwise diffusion. Therefore, I can neglect the streamwise diffusion in comparison to the cross stream diffusion, and the conservation equation just becomes a balance between streamwise convection and cross stream diffusion. Okay. Okay. In that case, the temperature field at a given location x, okay, will not depend upon the total length of the plate L, okay, because we have neglected streamwise diffusion. Cross stream diffusion only transports energy perpendicular to the surface. Streamwise convection on the left side only transports energy downstream, right. Therefore, the temperature at a given location cannot depend upon conditions at a downstream location, because for that information has to travel upstream, and in the equation we do not have any diffusion which can alter the temperature upstream. Because of that, the boundary layer thickness at a given location x has to depend only upon x itself. So, I should be able to write a similarity variable as y by delta of x. Once I do that, I insert it into the conservation equation and simplify, okay. And finally, I had got an equation of this kind. Okay. Okay, gamma dot delta square by alpha d delta by dx into minus eta square dt by d eta is equal to d square t by d eta square. And I said that the term in the red box has to be a constant if we require that a similarity solution is valid, so that the resultant equation depends only upon eta and not individually upon x and y. Okay. So, therefore, has to be a constant. We can assume any value for that constant. The resultant solution that I get in terms of eta will change depending upon what constant I assume, but if I go back to the original variables y and x, that solution will be independent of the constant that I assume. Okay. So, the simplest thing is to assume that the constant is 1, okay, without loss of generality. Okay. This gives us gamma dot by alpha d delta cubed by dx. Okay. Okay, and I show a factor of 1/3 here. Okay. Delta square d delta by dx can be written as 1 by 3 d delta cubed by dx is equal to 1. Okay. And therefore, delta cubed is equal to 3 alpha x by gamma dot, okay, plus some constant c. Okay. I just integrated this equation. Okay. Now, that constant of integration has to come out from the initial conditions. In this case, the initial condition is that at x is equal to 0, at this location where the heated section has just started, at that location the boundary layer thickness has to be equal to 0, okay, because the boundary layer starts only at that location. Okay. And therefore, with that condition, the solution for delta just becomes delta is equal to 3 alpha x by gamma dot whole power 1/3. Okay. Alternatively, if I take the value of delta by x, the ratio of the boundary layer thickness to the downstream position, I will get 3 alpha by gamma dot x square power 1/3. Okay. And this can basically be written as 3 times Beckley number based upon x inverse, okay, power 1/3. Okay. Where the Beckley number based upon x has to be gamma dot x square by alpha. You recall we had defined a Peckley number in terms of L as gamma dot L square by alpha. In this case, this is a local Peckley number, gamma dot x square by alpha. Okay. So, it is no surprise that if the length scale has to be x instead of L, the boundary layer thickness has to scale as the Peckley number based upon x to the 1/3 power. Okay. So, that is not surprising. So, that is one part of the problem, the solution for the temperature field for the boundary layer thickness. Okay. The other part of the problem is to solve for the temperature field. Okay. The temperature equation is minus eta square dt by d eta is equal to d square T by d eta square. Okay. This can be solved quite easily, okay, because this is a second order differential equation. I will get dt by d eta is equal to c e power minus eta cubed by 3. Okay. I will call this as constant, this is a constant of integration. Okay. And then T will be equal to a integral 0 to eta d eta prime e power minus eta prime cubed by 3 plus some constant b. So, let me just collect all the terms here. Okay. The original equation that I had to solve when expressed in terms of the similarity solution was of the form gamma dot delta square by alpha d delta by dx into minus eta square d t star by d eta is equal to d square t star by d eta square. Okay. With the boundary condition that t star is equal to 1 at y is equal to 0. Okay. Recall that eta is equal to y by delta of x. Okay. T star is equal to 1 at y is equal to 0, which is equivalent to eta is equal to 0. Okay. At the surface itself, T star was 1. Okay. T star was equal to 0 as y goes to infinity, which implies that eta goes to infinity. Okay. And T star is equal to 0 at x is equal to 0 for all y. Okay. At x is equal to 0, delta is equal to 0. We just solved that. At x is equal to 0, the boundary layer thickness is 0. What that means is that this corresponds to eta going to infinity. Okay. So, both x is equal to 0 as well as y going to infinity give you the same value of delta of eta. Okay. And you can see that these two boundary conditions reduce to the same when expressed in terms of eta. That is a fundamental requirement for a similarity solution. Okay. Now, the first part of the solution was gamma dot delta square by alpha d delta by dx is equal to a constant, so that the convection and diffusion continue to be of equal magnitude even in the limit of the Reynolds number going the Peckley number going to infinity. Okay. You can choose any constant because the solution in terms of eta will depend on that constant. The solution in terms of x and y cannot depend on that constant because that constant did not enter into the original equations. Okay. So, because of that, without loss of generality, I can assume this constant to be any value. Okay. And we had got the value of delta here, okay, was equal to alpha by 3 alpha by gamma dot 3 alpha x by gamma dot whole power 1/3. Okay. This was the expression for delta, okay, 3 alpha x by gamma dot power 1/3. Okay. So, this is the boundary layer thickness. Now, I have to solve the other part of the equation, minus eta square dt by d eta Now, to solve this equation, I just substitute w is equal to dt by d eta, okay, and I will get minus eta square w is equal to dw by d eta. I will get log w is minus eta cubed by 3 plus a constant, which means that dt by d eta is equal to w is equal to some constant a e power minus eta cubed by 3. Okay. And to get the temperature, I have to integrate this once again. Okay. T star is equal to a integral 0 to eta d eta prime e power minus eta prime cubed by 3 plus b. And these constants a and b have to be determined from the boundary conditions. Okay. These constants a and b have to be determined from the boundary conditions. At eta is equal to 0, T star is 1. Okay. At eta is equal to 0, this first term is equal to 0. Okay. Therefore, if T star is equal to 1 at eta is equal to 0, it implies that b is equal to 1. Okay. And as eta goes to infinity, the temperature has to be 0. Okay. Therefore, if you do that, you will get a temperature of the form 1 minus integral 0 to eta d eta prime e power minus eta prime cubed by 3 by integral 0 to infinity. Okay. So, that will be the temperature which satisfies both boundary conditions. At infinity it is 0, at 0 it is 1. Okay. And this can be evaluated in terms of error functions, I am sorry, in terms of gamma functions. Okay. This integral 0 to infinity d eta prime e power minus eta prime cubed by 3 can be evaluated in terms of gamma functions. It turns out that it is of the form 1 minus 3 to the 2/3 by gamma of 1 by 3 integral 0 to eta. Okay. And what that means is that the temperature gradient is equal to minus 3 to the 2/3 by gamma of 1/3, okay, the constant e power minus eta cubed by 3. Okay. So, that fixes the two constants. The condition that temperature is 1 at 0 and at 0 at infinity fixes the two constants. So, this is the solution, okay, where eta is actually eta is actually 3 alpha x by gamma dot whole power 1/3. That comes in the limit of the integration, okay, that comes into the limit of the integration. Okay. So, that is the temperature, the solution for the temperature field. Okay. And from that we can get the flux and therefore the heat transfer rate. Okay. So, back to our solution, T star is equal to 1 minus integral the heat flux q y perpendicular to the surface at the surface, okay, is going to be equal to minus k partial t by partial y, okay, at y is equal to 0. Okay. It is equal to minus k into T naught minus T infinity, okay, because temperature, if you recall, T star was defined as T minus T infinity by T naught minus T infinity. Okay. So, that was our definition of the scale temperature. Therefore, I get this term here, okay, when I express in terms of T star. Okay. And here I will get a delta of x, okay, and this whole thing has to be at eta is equal to 0. Okay. Recall that eta is equal to y by delta of x. Okay. So, when I transfer from y to eta, I get a factor of delta. Okay. So, that is the heat flux. Okay. What is dt star by d eta at eta equals 0? Okay. We had just evaluated that. Okay. This is the dt star by d eta. Okay. At eta is equal to 0, this term just becomes equal to 1. Okay. So, therefore, I just get, okay, minus k into T naught minus T infinity by delta of x, okay. And then I have a factor of minus 3 to the 2/3 by gamma of 1/3 e power minus eta cubed by 3, okay, whole at eta is equal to 0. This term here is just equal to 1. Therefore, my equation becomes k into T naught minus T infinity by delta of x times a constant 3 to the 2/3 okay. And if I use the definition of delta that I had earlier, okay, delta of x was equal to 3 alpha x by gamma dot whole power 1/3. Okay. So, this I will get k into T naught minus T infinity by 3 alpha x by gamma dot whole power 1/3, okay, into 3 power 2/3 by gamma of 1/3. Okay. So, that is the heat flux. It is a function of x, okay. It is a function of x, okay. And now, if I want to calculate the average heat flux, I have to integrate this heat flux all the way from x is equal to 0 to infinity. Note that the boundary layer thickness is increasing proportional to x to the 1/3 here, okay. The boundary layer thickness is increasing proportional to x to the 1/3, okay. Therefore, the heat flux is decreasing as 1 over x to the 1/3 in this case, okay. Now, the average heat flux 1 by L integral 0 to L dx q y. Okay. Now, this will go as 3 by 2 x power plus 2 by 3, okay. Okay. So, this term here, okay, okay, will give me and here I have 3 alpha by gamma dot power 1/3. Okay. This will give me one by L into 3 by 2 L power plus 2 by 3. Okay. Okay, so, continuing it over here, q y bar, okay, is equal to k into T naught minus T infinity. Okay. I have a 3 times 3 to the 2/3, that is 3 to the 5/3 minus 3 to the 1/3. So, I will get 3 to the 4/3. Okay. And this has to be divided by 2 times gamma of 1/3. Okay. And here I will get gamma dot by alpha L whole to the 1/3. Okay, because I get L to the minus 1/3 if I take these two terms here. Okay. That is q y. Okay. What is the Peclet number? Okay. The Peclet number is typically defined as 2 q y by k into T naught minus T infinity by L. Okay. This is for the flow past a flat surface. Okay. The factor of 2 is a factor that is put in by convention. Okay. Now, when I divide throughout by k naught minus T naught minus T infinity by L, I will get 2 into 3 power 4 by 3rd by 2 gamma of 1/3, okay, into gamma dot L square by alpha power 1/3. Okay. I am sorry, this is the Nusselt number. Okay. My apologies. What I am writing is for the Nusselt number, which is the independent variable. Okay. The Nusselt number is the independent variable in this problem. The non-dimensional flux is the Nusselt number that you get as some constant, okay, times Peclet number to the plus 1/3 power. Okay. That constant, if you work it out, it turns out to be about 1.61 times Peclet number to the 1/3 power. Okay. So, this is the correlation for the heat transfer for the flow past a flat plate. Nusselt number is about 1.61 times Peclet number to the plus 1/3 power, where the Peclet number is defined as gamma dot L square by alpha whole power 1/3. Okay. So, from the boundary layer equations we had got a solution, a similarity solution in terms of the similarity variable alpha. Once we had got that solution, we then calculated what is the heat flux at the surface, and from that we had calculated what is the average flux by integrating over the streamwise distance. Turns out the boundary layer thickness was proportional to the Peclet number to the minus 1/3 power, Peclet number based upon x to the minus 1/3 power. Therefore, the heat flux was decreased as x to the minus 1/3 power, and if you take the average over some length L, it increases as gamma dot L square by alpha to the 1/3 power, where the Peclet number is now in terms of the strain rate at the surface, gamma dot. Okay, it is not in terms of the mean velocity. Okay. Now, this analysis, it turns out, can be straight away applied to a pipe flow. Okay. Let us consider the heat transfer in a pipe, where I have at x is equal to 0, okay, the fluid is coming in with some velocity profile, and for x greater than 0 I have a heated section. Okay. The temperature is T naught here, okay, I am sorry, T infinity. And at this section the temperature is T naught. Okay. Therefore, in this heated section the boundary layer thickness will increase. As long as the boundary layer thickness is much smaller than the pipe diameter, you can consider the surface to be a plane surface, because curvature effects do not matter. As long as the temperature, the thickness of the boundary layer, okay, delta, okay, is much smaller than the radius of the curvature, it looks exactly like a flow past a flat surface. The analysis that we have done can be directly used. Okay. From this we will get that the heat transfer, average heat transfer flux is going to be equal to, okay, is going to be given by this relation here. Okay. K into T naught minus T infinity, okay, into 3 power 4/3 by 2 in the denominator, okay, 2 gamma power 1/3 okay, into gamma dot by alpha L to the 1/3. Okay. Okay, for a length L. Okay, for a length of pipe L, this is going to be the heat transfer, the heat flux. Okay. Now, for a pipe flow, we know that the velocity we had calculated is 2u, okay, into 1 minus r by r the whole square, okay, where r, capital R is the radius of the pipe and u is the average velocity. We had calculated this for a parabolic profile, okay, which means that partial ux by partial r is equal to minus 8 u r, I am sorry, by r square. Okay. Okay, there is a strain rate which is gamma dot. Okay. At the wall, gamma dot at r is equal to r is just going to be equal to minus 4 u by r. If I write it instead in terms of the pipe diameter d, this just becomes minus 2 u by d. Okay, because I am sorry, this okay, it is 2u by r. If I write in terms of the pipe diameter, this becomes 4u by d. Okay. Okay. And I can substitute that into my expression for the heat flux. Okay. Therefore, I will get Qy average is equal to k into T naught minus T infinity, okay, to 3 power 4 by 3 by 2 gamma of 1/3, okay, into 4u by d alpha L, okay, power 1/3. Okay. I should be careful here. This, I am sorry, this is 4, that is correct. When I take the derivative, I get a factor of 4. This is a factor of 4, and this one becomes a factor of 8, okay, when I express it in terms of the diameter. Okay. So, what I have here is a factor of 8. Okay. And this is just k into T naught minus T infinity 3 power 4 by 3 by gamma of 1/3 into u by d alpha L whole power 1/3. Okay. Now, the Nusselt number for a pipe flow is defined as Qy by k into T naught minus T infinity by d. Okay. It is scaled by the diameter, not by the length. For a pipe flow, this is scaled by the diameter. Okay. So, if I do that, I will get 3 power 4 by 3 by gamma of 1/3, okay, into u d by L power 1 u d by alpha. Okay. Into d by L power 1/3. Okay. I multiply throughout by the diameter on top. So, I get a d square power 1/3, which gives me u d by L power 1/3 times alpha power 1/3, which is d by L power 1/3. Okay. And if you evaluate this, this is approximately 1.61. Okay. Beckley number power 1/3 d by L power 1/3. Okay. Beckley number, we know this is equal to 1.61 Re power 1/3, Prandtl number power 1/3 d by L power 1/3. Recall the Nusselt number correlation for a pipe flow, okay, 1.86. Okay. We have got a relation that is almost exactly the same, except that there is about a 15% difference in the constant of integration. Okay. And that 15% difference is because we have neglected the curvature of the pipe. Okay. So, up to this constant value, we have managed to get the correlation for the heat transfer in a pipe 1.61, a constant, times Re power 1/3 Pr power 1/3 d by L power 1/3. Okay. This is because the heat transfer has to go as the Beckley number power 1/3 based upon the length. Okay. The Beckley number power 1/3 based upon the length, and when you write that in terms of the strain rate at the wall and the diameter of the pipe, you get Beckley number power 1/3 times d by L power 1/3. Alternatively, Reynolds number power 1/3, Prandtl number power 1/3 d by L power 1/3. Okay. So, I have shown you how to use boundary layer theory in order to get the correlation for the heat transfer in a pipe. In a similar manner, you can get correlations for other flows as well. Heat transfer in the flow past a particle, we will see in the next lecture, and then we will come back to a problem that we had already solved, the mass transfer into a falling film. If you recall, in that case, we had got the Nusselt number as Beckley number to the half power. In this case, we are getting it to the 1/3 power. The difference is, in this case, the velocity has to be 0 at the wall, and the velocity has to increase linearly from the wall. In the case of the mass transfer into a falling film, the velocity was finite at the interface between the gas and the liquid. How does that result in different scaling laws? I will continue that in the next lecture. I will see you then.